So you got a little bit of an intuition for what a sampling distribution of sample proportions is. We're gonna solidify that and just get some rules down for these in this section, and then we'll work on some problems that involve sampling distributions of sample proportions. So in the context of the candy machine applet, let's just make sure we understand the difference between these things. Namely, the distribution of the population, the distribution of a sample, and the sampling distribution of a sample proportion. So let's just talk about our first setup was P is 0.45, and that was the true distribution of orange candies, right? So that means the population would look like this. And this is categorical variable. So it's going to be a bar graph. And the bar graph would just have two bars. And so we would have orange, and that bar would go up to 0.45. And then you would have whatever other colors, and that one would go up to 0.55. That's everything else. And so that's what the distribution of the population of candies would look like. You'd have orange with the true proportion of orange at 0.45, and then every other color makes up 0.55 of the population. And then the distribution of a sample, let's say we did a couple different sample sizes, but let's say we took a sample of size 25. Would also be a bar graph. But in a sample, you're not necessarily, just because the population is 45% orange, that doesn't mean that when you get a sample of 25 candies, you're going to get exactly 45% of them orange, right? But let's make up a number. Let's say you could get 40% orange, and that would mean 60% would be other, right? And then we would call this P hat. That's a sample proportion of orange. And this is a sample proportion of other colors. And that would have to be 60%. All right. And then what's really important that we understand is what a sampling distribution of P hat would look like. And so that's where you take all possible samples of the same size. Let's say we're dealing with size n equals 25. And each time you take a sample, you compute, in this case, the proportion of orange. And you create a dot plot out of that, right? So in this case, my x-axis is sample proportion of orange candies, and lowest would be 0, biggest possibly could be 100% orange. But what we do know is that it should roughly sit over the true population proportion, 0.45, and we saw that it's going to be approximately normal. And so what I sometimes like to do is, instead of using dots, I'll just draw p hats to remind you that each one of the dots actually represents a sample proportion. And we would expect this to be, right, roughly normal. So I'll try and draw it to be approximately normal and center over the true population proportion, which was 0.45. And remember that what we were creating was not a true sampling distribution, but it was an approximate sampling distribution, because for a true sampling distribution, you would have to have every possible sample of that size. So in this case, size 25. Which, if your population is any triple digit number, the number of combinations to get a sample of size 25, goes into the billions. So it's like impossible to get a true sampling distribution. So oftentimes we're working with approximate sampling distributions. All right. I'm going to skip that slide. All right. This summarizes kind of everything that we've talked about so far. The shape of the sampling distribution of p hat can be approximated by a normal curve, and that depends on the sample size n and the population proportion p. The center, we say the mean of p hat is equal to the true population proportion p. This makes sense because the sample proportion is an unbiased estimator of p. And the spread for a specific value of p, we found that the standard deviation, which we'll call sigma p hat, gets smaller as your sample size gets larger. And the value of sigma p hat will depend on both your sample size n and your population proportion e. On the next slide, I'm going to go ahead and give you the formulas for these. All right, so there's a connection between the sample proportion p hat and the number of what we'll call successes in the sample, which is x. And the way we compute it is it's the number of successes divided by the size of the sample. So it's just x over n. So this is important to write down. P hat equals x over n. So like, if I wanted to compute the proportion of orange candies in a sample of 10, I would count the number of orange. Let's say it was 3. I would divide by the sample size, which is 10, and I would get my p hat as 0.3. Okay, so this next slide, I don't want you to write it down because it's not like important that you are able to rederive these formulas. I just want to show you kind of where they're coming from. So these are all coming from formulas that we had from our last unit on random variables. All right, so namely, for a random variable x, the way we compute the mean is by n times p, and the way we compute the standard deviation is the square root of n times p times 1 minus p. Those are both formulas that are in your formula packet that you will be provided on the AP exam. And since p hat is just x divided by n, it's just a random variable divided by n, that's the same as 1 over n times x. So all I'm doing is multiplying a constant by my random variable. So it's actually just a transformation. Therefore, to compute the new mean, we already know that if you're transforming by multiplying by something, the mean gets transformed by multiplying by that same constant. So to compute my new mean, I just take my n times p, I multiply it by 1 over n, and I'm just left with p, which I already told you in the last slide, but that's just where that fact comes from. So the mu of p hat is equal to p, which tells us that p hat is an unbiased estimator of p. I should say of, not or. And then sigma p hat, same thing. I'll just multiply through by the constant multiple. Now to sneak that constant multiple under the square root, the thing I'm going to do is rewrite it as, instead of 1 over n, I'm going to square it and put it under a square root. And then I can multiply it inside the radical. Simplifying, we end up with this formula. Sigma p hat equals the square root of p times 1 minus p over n, which makes sense that we would be dividing by our sample size, because as we increase the sample size, then that fraction will get smaller. As you increase the sample size, you're dividing by a larger number, which will make that fraction smaller. Thus, our spread gets smaller as our sample size goes up. All right. So here are the big formulas, the big takeaways from this first section. So I'm going to give you a chance to write that down. Mu of p hat equals p. Our formula for computing the standard deviation, sigma p hat, is root p times 1 minus p over n. Both of these will be provided in your formula sheets. And then we have this 10% condition. That we need to use to be able to actually compute the standard deviation. We kind of briefly talked about this in the last unit. It came up, but this is the 10% condition. It has to be safe to assume that the sample size is less than 1/10 of the population size. And all that does is ensure for us that the individuals in the population can be considered independent in our sample. So you can think of this as the independence condition. It's a little bit of a formality, but we'll begin checking it so often that it'll just become second nature. So you're just checking to make sure that the sample is less than 1/10 of your population. A quick way to do it is just multiply your sample by 10 and then just state that it's safe to assume that that's smaller than your population size. All right, and the final condition is the normality condition, and that's just that, can we assume that our sampling distribution is normal? And for that, we need to multiply n times p, make sure that's greater than 10, and then n times 1 minus p, make sure that's greater than or equal to 10. All right, I'll pause here. Give me a hand when you're good. So if you're looking at a sampling distribution of p, I just laughed because I don't think I ever noticed. I mean, I've had this slide for years now, but I don't know what reference this cool group of people is supposed to be. I guess they're supposed to be a sample of some kind. But if you take samples up from a population over and over again and commute some sort of a sample proportion, we know that it's safe to assume that it's normal as long as we check the normality condition. The mean here will be p. It'll sit over the true population proportion, and the standard deviation will be given by that formula. Let's do an example where we can actually use this information. All right, so the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a 4-year college or university. So the way they're stating that, that's the true population proportion. So P equals 0.8. What is the probability that a simple random sample of size 125 will give a sample proportion of at most 75%? All right, so I'm going to go, my sample size that I'm discussing is 125. And the question I'm trying to answer is, what is the probability that we'll get a sample proportion, so a p hat, of at most, so at most means less than or equal to 75%, so 0.75. So what's the probability that I get a sample proportion that's less than or equal to 0.75 if the true proportion is 80%? All right, so before I can do anything with a theoretical sampling distribution, I need to check my conditions for normality. So a couple things I'm going to do is go, all right, so what's n times p? So that's 125 times 0.8. Which is 100, which is definitely greater than 10. And then n times 1 minus p, it's 125 times 0.2, which is 25, which is greater than or equal to 10. So it's safe to assume that my sampling distribution will be approximately normal in shape. Now I want to check to make sure that the individuals that I'm sampling can be safely assumed to be independent, and that's that 10% condition. And so all I'm going to do is multiply my sample by 10, so 125 by 10. $1,250, and I'm just going to say it's safe to assume a large district would have more than 1,250 students. And that just, again, that allows me to assume that when I am sampling, the individuals that I'm sampling are safe to assume to be independent of each other. All right, so now I can sketch out my sampling distribution because I know it's going to be approximately normal. That was bad. Still not very good, but that's about as good as I'm going to do right now. So remember that what this distribution is, it's the distribution of values of p hat. So you can think of a bunch of little p hats underneath here, and each one is a sample of students, and it's a sample of size 125 where I'm just surveying how many of them are going to attend a university or four-year college. All right, well, what do we know that this should center over? What's the mean of this distribution going to be? What should be right in the middle of that? What's the true proportion of students who are going to attend a four-year college or university? There we go, 0.8. So we know that since p hat is an unbiased estimator, it should sit on top of the true proportion, 0.8. So I know that that's going to be right in the middle. I also can compute my standard deviation. I know what that's going to be. That's going to be the square root of 0.8 times 0.2 over my sample size, so over 125. Awesome. So I know I have a normal distribution whose mean is 0.8 and whose standard deviation is that square root. I should be able to make a computation for what they're asking me. What's the value, what's the probability that p hat is less than or equal to 0.75? So 0.75 is going to be somewhere to the left of 0.8. I'm basically looking for this area. Do you guys remember the function in your calculator that lets you find area on an interval under a normal distribution? Other one. Inverse norm is the one where you input the area and it gives you back the boundaries. That's it, normal CDF. So we're going to pull up normal CDF in our calculator. Sorry, it takes my calculator a second to open. Okay. So I'll go, that's in distribution, so I'm going to go second vars. It's the second one. It's normal CDF. My lower boundary is technically negative infinity, so I'll just go negative 999. My upper is 0.75. My mean is 0.8. My standard deviation, you can actually just put the calculation in there. Your calculator can handle it. So it's the square root of 0.8 times 0.2 divided by 125. There we go, 0.081. So the answer to my question here is 0.081, or about an 8% chance that if the true proportion of students who are going to attend a university or four-year college is 80%, that she chooses a sample of size 125 where less than 75% say they're going to attend college. All right, we're going to stop there. You can work on the problem set because it doesn't involve any of what's in this last example. So please do work on the problem set. I'll take questions over it next time. And then next time we're going to do sampling distribution of the difference in sample proportions. And we'll just do an example of that in our notes, and then we'll do the formative assessment. So I'm going to push back 7.3 until next week. But that's what you can expect to do next class.